Hello everyone. In this video we will continue to examine topic 4.4 wave behavior, and in particular we will continue to examine the phenomenon of double slit interference, path difference, and the quantitative analysis of the double slit interference pattern. All right, so to quantitatively analyze exactly the relationship between the interference pattern and our conditions for constructive interference and destructive interference, we need a couple of diagrams. So in IB notation, we're going to call the fringe spacing S. So the fringe spacing S is the difference, or is the space between the bright lines. So in the bright line patterns you can see over here, the fringe spacing S would be this distance, and this one, and this one. So it's the difference between any of the bright lines. We'll call the screen distance, or sometimes just distance, that capital D, as the distance to the viewing screen. And that, in IB notation, uses a capital D. The slit spacing is the distance between the slits, the small distance right here between the slits, or also seen on this diagram here, that's little d as well. I apologize for the fact that this notation can be confusing, particularly when we start to read out the equations, given the fact that there is a capital D distance and a lower key d distance. Also, two of the quantities are known by spacing, so that's confusing. And I am going to be using some, I think, pretty illustrative diagrams that nevertheless name the symbols differently. So this all makes things a little bit confusing. Just keep track of the fringe spacing, the distance to the screen, and the slit spacing. All right, here we go. So the first thing to recognize is that this is our big picture view here. Notice that the distance to the screen, shown as L in this diagram, but the same as the distance right there, is big. It's really big relative to the slits. So the slits are sometimes millimeters apart. L is usually a meter. So it's about 1,000 times bigger. And even in this diagram, this angle is greatly exaggerated so that we can see what's going on. We're going to focus in on points of constructive and destructive interference at a particular angle theta to the original slits. So theta is shown in this diagram as here, and you'll notice that if you zoom out far enough, there is no real difference in terms of theta between the angle made by R1, the distance from the first slit, and R2, the distance from the second. So if you sort of zoom out on this diagram big enough, you'll see that this triangle is very, 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 very skinny triangle, and therefore the angle theta is about the same for both. That's important. The second thing to note is to observe this particular geometry. So the distance between the central maximum indicated here is y equals 0 to that first point that we're going to talk about is L tan theta for whatever theta happens to be. So we'll use that in 1 second. Now zoom in. Zoom in, zoom in, zoom in, zoom in. From the perspective of sort of this bubble right here, okay? So we're zooming in right next to the slits, all right? From the perspective of right next to the slits, we're going to assume something which seems a little bit incompatible with what I just said. But remember, this is a very, very, very skinny triangle that we're talking about up here. And the assumption we're going to make is that if we're this far zoomed in, the assumption we're going to make is that R1 and R2, the light coming from both slits, are from this perspective basically parallel. Okay, they're close enough to parallel when we zoom this far in that we can call them parallel if all we're doing is looking at this diagram right here. And so we can zoom in on this and notice our slit spacing is small d, and this is our angle theta. But two more things that we get to say. One is First of all, notice that this theta right here is the same as this theta in the triangle made between R1, R2, and delta R, the path difference. That's the extra distance traveled by R2. That's the path difference that matters for getting that first dark spot or first bright spot. So that's the path difference. And if we sort of highlight this, okay, this is as if they were starting at the same point. That's the extra distance traveled. Then the key ingredient to notice is that this theta right here, the angle to the screen, is the same as the angle to the path difference, or to the edge of the path difference, basically. And that you can see with interior angles from geometry. There are a couple other ways to do it, but that relies on R1 and R2 being basically parallel, which you can see from this perspective, if we zoom all the way in, is pretty convincing. Now, we're going to put all those things together, all right? So, in our first triangle, diagram A, this is our diagram corresponding to this particular picture, except using the IB labels for the notation. And the distance to the screen, from the slits to the screen, makes an angle, theta, to that first bright spot, okay, here, shown by S. S, remember, is our fringe spacing. It's the distance between the bright fringes. You can always come back and look at this diagram if you need to remind yourself what the different variables are. Notice that this distance is D, the distance to the screen. And then we're going to do something really funny, which would bother all of the geometers in the room, which is that we're going to say that this distance is basically big D2. Okay, so we're going to use what's called the small angle approximation. Remember that drawn to scale, this triangle, the same as this one, is very, very, very skinny. So remember that big D, this number right here, is 1,000 times the rough size of this small s here. Small s tends to be in millimeters or at most a centimeter. Big D is meters. So this triangle, the one that we're assuming, where this D is basically the same as this D, looks like a tiny, skinny triangle. I can't even draw it here. And so we use what's called the small angle approximation. You can check this in radians if you like. We can say that tan theta is about equal to sine theta, and therefore sine theta is about equal to S over D, and all those things are about equal to theta, okay? So this is our small angle approximation where the tangent of theta, S over D, is about equal to the sine of theta, S over D. Notice the same approximation. Awesome. Then we use the other triangle. We use a triangle in the second diagram with the same theta. So we're using theta to unify them. And we look at this particular triangle right here and we say, all right, well, if I draw out that triangle, then my path difference delta R is that small difference here. The slit spacing, so the distance between the two slits, is shown with little d, and this is the same angle theta. All right, so now we're equipped to get the equation that we need. We say the path difference for constructive interference occurs at an integer number of wavelengths, n lambda, and therefore the path difference is equal to d sine theta. Notice that that comes from this triangle, from triangle B. So d, little d, times the sine of theta is equal to this far side of the triangle. Another way of looking at it is saying that sine of theta is equal to the opposite, PD, over the hypotenuse, little d. And so if sine theta is equal to PD over little d, then PD equals d sine theta. So we plug that in. And then we use the fact that sine theta is about equal to the fringe spacing divided by capital D, the distance to the screen. Therefore, D times S over big D is about equal to n lambda, which means that the fringe spacing in general is then governed by this equation. Little s, the fringe spacing, is equal to lambda times big D over little d. Notice that if you're talking about the distance between more than one fringe, so for example, the first fringe and the fourth fringe, you can just multiply this by n. So that's where the n went. N is sort of hidden here. But this is the equation given in your data booklet, and it refers to the distance, s, between the bright fringes, and that depends on the wavelength, the distance to the screen, and the distance between the slits. At minimum, standard level, you should be very comfortable using this equation, although you do not need to derive it yourself.